So hello everybody from the Zoom. Today we're going to keep going on troubleshooting. So I need to share. So last time we talked about some of the various methods for process troubleshooting, looking at the really basic, treating the symptoms, identifying the cause and addressing the cause, which sounds helpful, but really isn't very organized. Fogler and LeBlanc have this approach, looking at this 5-step method where you first define the problem, generate various ideas, decide the best solution strategy, implement, and then evaluate. One of the things that can be really important in a troubleshooting system is continual evaluation of the process, right? Because at the end of the day, problems are going to continue to arise. They could be perpetual. And if so, you may have thought you've addressed an issue, but maybe have only suppressed it through treating symptoms. And that's why it's important to not just treat symptoms for a process, but also make sure that you actually identify the root cause. That's a big part of why on Friday we talked about finding the why of the problem so that you can find a more permanent solution. So I think this is kind of where we ended up looking at this absorber system, reducing an acetone concentration from 40 millimoles from 0.02 to 0.01. But then you notice over time that the acetone concentration is going to be increasing by 0.008. And so just like a quick recap, looking at this, the acetone absorber where we see increasing concentration of acetone leaving in the air outlet, where our base case had the acetone concentration going from 0.02 to 0.001. Double check that. And now our new case, our YA out was about 0.008. So an 8-fold increase in the outlet concentration of acetone. We had discussed various ways to address it. Looking at changing for potential solutions. We can change the column conditions. And what I mean by conditions is the temperature and pressure. We can manipulate the flow rates. Our airstream and our liquid or our solvent stream, which was water in this case. You guys remember which one we said was the best, most effective way to treat this symptom? Water. Was to increase the water flow rate. So the most effective solution was to increase the water flow rate. All right, so let's take a look at a few more today, starting this one. We have a problem associated with feed pumps to a cumulative production process, where we notice that bearing failure is occurring on P802, with P801 having been operating normally without issues. And we notice that the last known issue occurred during a heat wave when the ambient temperature rose to 105 Fahrenheit. Suggest possible causes for the problem. So I'll let you guys write that down. And then I want you guys to think about some ways in which we can take a look at this. Make sure I get to the right there. All right, I'll give you guys some time. So let's take a look at this. This is involving bearing failure on feed pumps. So what's the first step in looking at this issue? See how much you guys remember from Friday. What's the first step? Looking at a troubleshooting. Treat the symptoms unless it's dangerous. All right, that's one way. What's the best thing to do first? Verify or identify the problem. So in this case, what is the problem?
Or deep temperatures go hot before we most likely from whenever I call that ambient temperature, it's most likely caused.
Well, see, now you're doing what I call jumping to conclusions. What was the problem in the system? The bearing is failing, and that might seem silly, but it's important to write out just what is the problem. Because like I said, you might be dealing with a very large team, you might be dealing with people that aren't chemical engineers, and you want to make sure you're all working on the same problem. And so, like I said, I'm going to say, what's the problem? I'm going to say bearing failure. The other guy's gone to get ice. The other guy is going to over in the tower. You got to make sure you're all looking at the same problem. So step one is identify / verify the problem. So I will say bearing failure noticed P802 and P801 is operating fine. I'll rewrite that to make it a little more neat. All right, what's the next step? Step two. Step two. Once we identified the problem. Verify process conditions. Check parameters, right? So this is the gather data. You can verify process conditions. And unit operation performance. All right, so what information may you want to check? May we want to know for the system?
Well, since you're working with the pump, make sure that the pressures haven't changed greatly based on what they were before. Right?
Can you repeat that? I'm sorry.
So just make sure that the pressures around the pump on the streams and the outlet haven't changed much.
Okay.
They were.
So you can verify pressure conditions on inlet before and after pumped. Okay, is there anything else we might want to know?
Flow rate of the feed for.
Okay, so the flow conditions, process flow rates. Right, what's my stream table look like? Anything else you guys might want to know?
I don't know how close we were operating before the calculation was.
Okay, so you'd be interested in NPSH A data or A available versus required. Okay, what else? Go ahead.
With the temperature that went down at the pump.
Temperatures in and out of the pump. All sorts of information. Anything else? You're gonna have like a good grill session with the operators. Go for it.
If they missed like maintenance on the pump.
All right, what's my maintenance log look like? Yeah. You want fluid level data? Okay. All right, I think we got a good list. What are we gonna do next? Now we got our laundry list of things to run around the plant to get. Checking everything, getting data logs, checking the maintenance, all the fun stuff. What are the potential causes that you guys think for this bearing failure? You- Let's see if anybody on Zoom has an idea. They've been quiet. We should put them on the spot. Who wants to volunteer?
What was the question again, Dr. Lopez?
What are the potential causes for the bearing failure that you think that you can think of? We're brainstorming. Increase in vapor pressure. Okay, cool. Any other ideas? All right, what about you, Reed? Do you have any ideas? What could be causing this issue? I do not. Got it. All right, can you help him, Joshua?
So I would think just over time, if you don't properly maintenance, but I guess that'd be part of the maintenance loan.
All right, so you think it's just wear and tear, improper maintenance?
Right. Not greasing the bearings and that kind of stuff.
All right, somebody forgot to change the oil, that kind of thing.
Right.
All right, so we got a few. So potential causes. So improper maintenance. We got, what else do we see? Increase in vapor pressure. pour installation. Anything else? Yeah. Such a leak in the line. All right. Go ahead.
Maybe the pump's already operating too close to the point of maximum operation, so that fluctuations in temperature cause capsicum issues.
Okay. So we're working the pump too hard. All right, flow rate too high. Now we've got corrosion to worry about. Oh, goodness. We let our inner hypochondriac come out. Anything else? When good plants go bad. What else? Or is that good? So then my question is, improper maintenance, increase in vapor pressure, poor installation. Can we do any sort of checking with any of this? Or is this something that we're just gonna have to go doing in a plant? What do you think? Which of these can we actually investigate without actually being in the plant? I'll give you an easy step. We can't really check corrosion. We can estimate it if we have no materials of construction, what material it's made out of. But we covered vessel design last week, and you guys did an excellent job. You guys had a corrosion allowance in there. So I'm going to say that that's probably something that we're not going to check. What's something that we want to check? What do you guys think might be the most likely cause? I know you guys are probably leaning towards something. What do you think? Maintenance messed up. Operator's fault. It's always maintenance. I'm going to get Mike in here. He's got some explaining to do. Look at flow meters and indicators. All right. Well, one thing that we can actually check is looking at the influence of vapor pressure in this system. Because it was told in the problem statement that the issue happened during a temperature rise. And so if I was going to investigate this, I would look at that system and I would find P802 is running from a propylene storage tank into our facility. And the propylene is stored in a vessel and it contains a liquid at equilibrium with vapor above it, right? So it's sitting in as a saturated liquid. So knowing it's a saturated liquid, I can say, well, if the temperature is going to influence this, what do you think it might be wanting to cause? What's going to happen to this system if the temperature rises? I have a tank, saturated liquid, vapor in the headspace, pump running up the bottom of the process. What's temperature going to do? All right, so the temperature is going to cause it to vaporize a little bit, right? And so we're going to see an increase in pressure due to more vapor being formed. Okay, so I buy that. I'll buy it. I got a coupon. It works. So what's that going to do to the system? What should I look at a little more closely then if I'm seeing the pressure being manipulated? Well, I'm probably going to want to take a look at NPSH and see if that's going to be changing with the function of temperature in this estimated in pressure. So we said NPSH is 1 over G, P minus P star over rho minus U squared over 2 minus head loss plus or minus delta Z, depending on what day of the week it is. If we're doing it right, since I put the pump below, let's really hope that's a plus. All right, so which variable is going to change when the temperature increases? So P star is going to increase with temperature. What does that mean for our NPSH? What do you think? It's going to decrease our NPSH? You guys buying it? Skeptical? Learn not to trust me? Maybe. So NPSH should fall. Is there anything else going to be increasing though in this system? Well, what did we just say up here? We said that the tank pressure is going to increase. So what's that going to do in our system, on our equation for NPSH? Well, what it means is P is also going to increase. And it's going to increase to the same extent. If I have a tank and it's at saturation, P will always be at P star. And so for the system, what I really have is this. I'm storing it as a saturated liquid. The temperature goes up, temperature goes down. If I'm considering it saturation, the pressure is going to correct itself. Temperature goes up, I have more vapor, pressure in the tank increases too to match the vapor pressure. Tank goes down, vice versa. What might be changing more so then? We might be missing something. So you might have a change in density, your velocity might change, maybe a little bit, but I don't think that's going to have a significant impact to the point where I'm going to be worrying about a bearing suddenly failing. Not saying it's not possible, I'm just saying it's not likely. We're missing a term here though. All right, so now we have 2 left. I'm saying it's not velocity, it's not pressure, what could it be? Ah, where does the vapor come from? There it is. If my temperature is going to increase and I'm going to have more vapor formation in my tank, vapor has to come from somewhere. Therefore, it's going to come from the liquid. What's that going to do for our liquid level? It's going to drop it, which means the static pressure going in is going to fall. So an increase in temperature may result in a loss of static pressure or static head and NPSHA as a result. This may lead to cavitation and bearing failure. And so the purpose of this problem in the exercise is that a lot of times looking at our key expressions can give us clues about what would and would not cause issues we see in a process. In this problem, the kind of easy answer is to say, well, the temperature rose, which means there's more vapor. We're closer to the vapor, boiling point. I expect the vapor pressure to go up, which is going to cause cavitation. So, bad system. But looking at the expression, we realize that the vapor pressure really is irrelevant if I'm storing it at saturation, which in a lot of tanks, especially if you're looking at organic, a lot of times how they end up being stored. But there are implications around it when it comes to temperature. And so if this is the case, what's the solution? How do I fix it? How do I fix it? You guys don't know? First you're blaming maintenance, now you're gonna have to call maintenance. Increase the liquid level. Make a note on the process that liquid level may need to be increased during warm weather. And adjust the low level alarms during warm weather. Now, in all likelihood, a well-designed problem is going to be over-engineered such that this is going to be taken into consideration before it's actually installed. However, in the real world, a lot of times things aren't designed properly. So that's when these kind of things happen. And so the simplest and most effective solution is increase the liquid level, increase the static head, and see if that addresses the issue. The bearings no longer wear out, then you most likely found the issue. If it keeps happening, then you're going to have to consider additional issues. Like it could be just corrosion, bad maintenance, a bad pump, right? Material defects do happen, and those sort of things. Any questions on that problem? How do you guys feel doing some troubleshooting? It's a lot of students kind of don't like it as much as some other problems that we do or that you do, because there's no one answer and there's no really awesome solution in a lot of it. A lot of it is this is how it would go forward, and you go forward. And so if you're a person that struggles with not having the like best solution or the answer, hitting the calculator and crunching the numbers, I'm sorry. It gets a little vague and a little more nebulous. Do you have a question? Well, that really depends on the size of the tank. Because it might have got to, what is it, 105 degrees, but there's a lot of things that can come into play with that. Was the tank insulated? What was it made out of? Because that's ambient temperature, and that doesn't even include radiant energy. And so the temperature on the inside of the tank might be completely different. And if it's not regulated, which it should be, but I don't know, lowest bid is lowest bid, I guess. And so it could be a lot hotter. And if it's a lot hotter, you could be looking at other issues. Right. And so if it's not a extremely large tank, you might have significant fluctuation. All right. No, that's a fair question. Definitely. Let's take a look at one more today. Well, I don't want to do that one. Let's do this one. I'll give you guys a minute to read it, and then I'll read it. This one involves a safety issue, a little bit. Flash fires are no fun. Let's see what we can think of to fix it. This one's a tough one. Missed the rest of it. I think those missed it. All right. So simply put, heavy naphtha process uses hydrogen in production. However, there's a point in the process where we have this heat exchange happening, and in it, there's a flange that fails to seal properly, such that over time, every once in a while, you'll get flash fires, meaning hydrogen's going to leak out, auto-ignite because it's so hot. And unfortunately, that's probably not one of the best things in the world. And the plant managers have finally decided we probably shouldn't have flash fires happening in our plant unless we want it to burn down. And so they decided to shut it down, and it has to be fixed. Maintenance is doing all they can on this flange, but they just can't seem to get it tight enough. So in this instance, definitely safety issue, right? Flash fires, and that's probably not good. And so the unfortunate, without fixing it immediately, the safe part in this instant is a plant shutdown. Because you can't operate this as it exists currently without having the hazard present. So $10,000 an hour every time this plant's not running, but it has to be fixed, and it has to be fixed quickly. So I'll do the easy parts, and then I want to see you guys' thoughts. Let's have a good discussion. So this is the heavy naphtha production and flash fires. I'll identify the problem. Which is heat exchanger flange. fails periodically, resulting in hydrogen fires. So what do we do? What are the potential causes? And I think this is if I remember reading this, it's was a heat integration preheating the feed. So it looks like this. You're preheating the feed with the products, reaction on the platform. And a seal around that heat exchanger, one of the flanges is just leaking hydrogen out. So what are we going to do? All right, what are you guys thinking? Any thoughts? Concerns? Right. All right, so we want to gather some data. Proper flange. What other information do we want?
Probably the temperatures of the reactor effluent and not the feed of all the relevant.
Okay, the relevant temperatures. What else do we want to know? Go for it. How what? All right. What kind of gaskets we got? Anything else? Any other information that we would like to know? Is that all you guys want to know? You're already ready to solve the puzzle? Pressures? Okay. Excuse me, the duty? Okay. Heat exchanger duty. All right. Anything else you guys want to know? You guys got it. All right, so what could be causes of this problem? Brainstorm. Man. Any ideas? Any thoughts?
So maybe the pressure on that flange is too high,
Pressure's too high on the flange.
causing it to leak.
All right, I'm gonna go ahead and say it too. Temperature is too high. Causing thermal expansion of the flange joints. And you just can't get it back down. Any other ideas? Is it just off spec, poorly designed? Who did this? Must have been a freshman. You guys want some of the old goodies? What did we say? Corrosion, poor maintenance. Operator error. The usual. Is there any other processing condition that you might think would cause this? Well, seems to be centered around the heat exchanger and a seal on that. So we're using the products from the platformer to preheat the feed of the platform. And the temperatures involved 500 degrees Celsius and 4.8 megapascals. And the plant manager is claiming that there's thermal expansion happening in the system. And that, you know, it's bound to happen because hydrogen is what hydrogen is. So the manager's claiming that it's a mixture of this with a little bit leaning on the temperature. The question then is, in 5 minutes, how do we fix this problem? How do we keep the fires from happening and get the plant running again? May not be $1 million question, but it's a $10,000 per hour kind of question. How do we fix it? You guys have any ideas? Or no ideas? You're just running head for the hills. This plant's doomed. Updating my resume as we speak. You guys just need more time. I'm putting you on the spot. All right, I'll tell you what, it's 10:46. Why don't we pick up here on Wednesday, see if you guys have some thoughts. And I will